Hi, and welcome to another episode of Integrated Science. Today we are continuing to talk about our ideas of motion, and we're going to add in, as you can see, the idea of force. How does force play a role in how objects move in motion in the free space around us? So far we've talked about the idea between scalar and vector quantities in relation to our speed and velocity. And then we applied the next layer of acceleration, how objects can either speed up and slow down or accelerate by going faster or slower. And then our three components to acceleration, which is the speed an object is traveling, the direction, or then is it changing direction, or is it one or both? That kind of go along with that. So we're going to add to that today. So you are going to want to get out a sheet of paper and take some notes along with what we're talking about. Remember, it's always important to at least get down what is underlined. Those are the types of concepts that you will see on formal assessments and everything as we move through. So no equation today. I will show you one, but you do not need to, we won't be using it. We'll just be as more of a concept to kind of explain things. So without further ado, let's talk a little bit about our different types of motions and how forces act on that. So the big thing that happens as we start to talk about how force is being applied on an object is we have to understand our differences between mass and weight. And so most of the time in this class we are going to use the term mass, but weight is something that you probably will commonly say, well, what's the weight of that? And you'll hear me say mass, and you'll be like, okay, I get it. So on Earth, mass and weight are pretty much the same because the gravitational force that is acting on us is the Earth, and it stays the same. However, if we were to travel to the moon, which we have, or to Mars, which we haven't, but we were supposed to in 2020. I don't know if it's going to happen, but maybe. I'm holding on a glimmer of hope that they still have another rover going there. Sorry, but humans have definitely not been to Mars or any other planet. So we've only been to the moon. Once again, is that our mass actually can vary. Our mass stays the same, but our weight can vary a little bit because the gravitational pull of those different objects changes. And so mass is the amount of matter an object is made up of, and it never changes. So it's what all the particles and the atoms and everything that gravity is pushing on, it stays the same. However, your weight is just dependent on gravitational forces. And we can even see that slightly change here on Earth. If we were to have you step on a scale just at maybe like say 0 sea level, so at sea level, maybe you will register at 100 pounds. And then let's say that I have you climb to top of Mount Everest and with your scale, you and your Sherpa and your scale, and you're at the top of Mount Everest, you put the scale down, you stand on it again, and it only registers as like 98.6 grams or kilograms. That would be crazy if you were just grams. So the gravitational pull is a little bit different at the top of Mount Everest versus at sea level because there's more gravitational pull pushing on you as you get closer and closer to the center of the Earth. So the force of gravity pulling down on you. So we can see that fluctuate even here just a little bit on Earth, but mass is something that is normally not going to change because it's what is that is made up of you or my cell phone or this marker, whatever it may be, versus weight is what is actually acting on the marker. And we can even pretend like it's weight. Is it weightless for a minute? Who knows? So how can we figure that out? And that's what we're going to do today. So mass versus weight. Force. So force has to do with just what kind of I was talking about there, is that we always have a gravitational force acting on us, which is a push or a pull. In this case, it's now pushing on you. You might be seated right now, so think about gravitational pushing on you. But we can also have it as a pull too. There's different types of things that can cause things to stretch out just ever so slightly and kind of compress. We'll talk about way later on when we get to the space unit something called gravitational waves, which is sent way out in space from a black hole that actually causes the Earth to go back and forth, and it makes that exact noise. Just kidding. It does make a noise though. I'll talk about it. If you're interested in it, just Google it. There's plenty of information out there, but ever so slightly it causes the Earth to pulse just a little bit. And that's another gravitational force acting on us. So a force can cause a motion of an object to change. Gravity is a force. If I were to push you, that would be a force. Or if I were to pull a string, or let's say that you're sitting in a wagon, I pull you, that would be a force too. So we can apply forces to objects when two objects come into a collision. Can't talk. They could also cause a push and a pull too. So we are going to look at this force in depth as we talk about Newton's 3 laws of motion. So it can be gravity, but it also can be other things that we can make too. You can even think about your body as a system of forces. Your heart is pumping blood all throughout your body, which is causing a force, a push and a pull. Is it push, pulls back and forth, back and forth. You can also think about just like your arm in general, is that you have a bicep and your tricep, and that when you contract and release it, that's a push and a pull. It can cause different types of movements in your body. So we can look at this on a grand scale of something huge like the Earth in the solar system, or we can look at it really small as things in our bodies, and then even smaller as we get into talking about subatomic particles. How do the protons and the neutrons affect the electron to even cause just small little electrical forces and electrical fields? So a couple of different terms that we're going to talk about. The first one is a net force, and that is just when two or more forces acting on an object at the same time. It's the total value of how much force is being applied to an object. So right now I'm sitting in a chair. Gravity is pushing down on me, and the chair is pushing back up on me. So I'm not falling down to the ground or anything like that. It's just allowing me to sit right here. It's technically, it's trying to make me accelerate. Like if I were to pull the chair out from under me, I would accelerate right to the ground. So when this happens, the object accelerates in the direction of a force. And we'll actually do a couple simulations where you'll knock an object into another one. And if it's stationary, how does that move? Or if you have two coming together, I guess I should do two fists. What happens there? How does that net force affect everything into place? So two or more forces. What's the total value of energy moving throughout the whole system? These are example of what we call free body diagrams, and they're very similar to, if you remember back when we talked about our motion maps, and we had our vectors, which is our arrows that are showing direction, and then instead of a dot that we represented as our object for forces, I normally use, or in physics we normally use a box. So these are different examples of free body diagrams, which is just showing how forces are being applied. And as you can see, this one says F tense. This stands for tension. So imagine it's like hanging from something, and then obviously gravity is pushing on it. So you have 1,200 newtons. N stands for newtons. That's our unit of measurement. Sir Isaac Newton, that is where that comes from. And then you have gravity at 800 newtons. So this is still being held up. So imagine if I was like holding on and trying to do a pull-up, which I'm terrible at, but I'm holding on to the bar. I have tension, and so therefore this is much greater, so gravity is not great enough. That's causing me to fall. This is kind of the flip scenario. So we have 600 newtons here and 800. So this object is falling towards the ground. And then finally, if we look here, we can even add on another layer. We've got right here. So think friction, normal forces, and then gravity here. So we've got gravity and normal forces at both 50 newtons, so they're equal. So imagine this is something maybe that is sitting on a table, and then we have frictional forces that are acting on it, dragging it. So imagine like maybe I push a book across a table. It's not going to fall through the table, nor is it going to rise up into the air, but it is going to come in contact with the table and slow down over time, and that's what this one's kind of representing. We'll get used to looking at those as we move through. Balance forces is just when an object is balanced, meaning that it's stable, that the forces actually equal each other. So a net force, where two forces cancel each other out and they're balanced. So if we look at the girl on the swing, we have 255 newtons here. Sorry, 245, and then 245 newtons here. So if we were to add those both together, we get 490. And that's what's also pushing down on her. So she's balanced in the swing. Each string is holding a portion of her weight, and gravity is also pushing down, and it's balanced. So the swing's not broken and she's not falling off or anything. An unbalanced force is just one is greater than the other, which causes motion. So balanced force is normally something that is stable or that is moving at a constant velocity, and an unbalanced force is one that is one is greater than the other, and it causes an object to become unbalanced. So if I push something, there's an example here of two students are pushing on a block in opposite directions. So think of like a tug-of-war contest with a rope would be a great example of something of this, where there's always going to be maybe something stronger or weaker, or one with a greater force, one with a lesser force than the other. Friction plays a major role in how objects move in motion and how forces are being applied. So friction is just a force that opposes motion. So here on Earth, we always have frictional forces because we always have gravity pushing down on us some way, shape, or form. So we can have air friction. Obviously, you might remember from previous presentation that I went over, I talked about Lightning McQueen on the dirt road and how his frictional forces change from what he was used to being on a paved road. So frictions occur because the surface of an object is rough. So even something that looks really smooth like ice still has some friction. You lose a lot though when you're on ice versus as if you were on something that was sand or gravel. So frictional just causes objects to move slightly different. The friction can cause a balanced or an unbalanced force, meaning that let's say you're on a paved road and you hit a patch of ice, that frictional force is going to allow that car to slide further because there is less friction, there's less roughness on the ice, which allows you to kind of slide back and forth. And we'll do some simulations here where you'll kind of get to see that just a little bit. So let's talk just a few minutes about Newton's first law of motion. There's three of them, and we're going to go all in depth in all three of them just so that you fully understand them completely and how they align with motion. And then we'll kind of move into how does that affect energy. So Newton's first law of motion, though, it has a nice little saying to it. An object in motion stays in motion. An object at rest stays at rest. And that's something that you've probably heard before. And so once again, we're just kind of applying different concepts to it. So motion, unbalanced, no motion, balanced. And that's what we're going to be looking at is how can we show objects that are in motion and give quantitative and qualitative values of how they are balanced or how they are unbalanced. And so sometimes you'll actually even hear Newton's first law of motion called inertia, which is just the idea that it wants to keep on doing whatever it's doing. So an object that is not in motion wants to stay not in motion, and an object in motion wants to continue in motion. However, there are opposite forces acting on it, which then jumps it into Newton's second and third law. So inertia is the tendency of an object to resist any change in its motion, in its net force. So think about those are all the forces acting on an object. So if an object is moving, it will stay in motion. It wants to be unbalanced, and that's kind of what I just said a few minutes ago. An object in motion, it wants to stay there, it wants to stay unbalanced, except that there might be some type of force acting on it. And if an object is at rest, it wants to continue to stay at rest. It wants to stay balanced. So here's some examples. A bowling ball and a table tennis ball. The inertia of the objects releases are different in its mass. So if we were to roll them, we would see different types of motions, or we might have to use different types of forces to kind of get them moving. And this all leads us into our assignments that we're going to be working on how to figure out what's balanced and what's unbalanced.